endochondrial ossification. You look at that inside, chondro meaning cartilage. This goes mesenchyme, cartilage to bone. This results in long bones and short bones. Okay? Now, let's talk about them in the order I've got them here. Intramembranous, that's what I've got up here. And this is not, I've hunted around a number of times over the years. I probably need to look again. There's not images that really show really, really good intramembranous. It's more of a concept, but I want to have something up here to point to things as we're describing it here. Intramembranous ossification results in flat bones, and flat bones are spongy bone with cortical bone on the outside. Okay, that's what we look at here. First thing that happens here is we have mesenchyme, and that's not shown where it's just mesenchyme in this image here, but here's my mesenchyme, and that mesenchyme will get increased vascularization of normal mesenchyme, and when that happens, some of the mesenchymal cells will shift into osteoprogenitor cells, which will shift into osteoblast. Osteoblasts then begin to lay down bone. Here you can see them laying down the yellow bone, and some of them get trapped in the bone and become osteocytes. Okay? And then we go from a high power magnification where we're looking at cells to a low power magnification where we're looking at the structure, not seeing the cells here and here. That's why I say it's not as good of a drawing in that way. You can't get the idea. But basically what happens is that once we start to make the bone, we now have to, I'll say sculpt the bone. Osteoblast laying down bone, osteoclast taking up bone. We now have to sculpt it to make spongy bone. You see it's still surrounded by mesenchyme. Blood vessels will come in here as that process is happening. And then eventually we'll lay a small layer of cortical bone, have the spongy bone in the middle. Here's the osteoblast laying down the cortical bone. They should have had some osteoblast here. These are much larger compared to the bone they're laying down here. But this is basically what flat bone looks like. It's got a thin layer of cortical bone, spongy bone in between. There's some sources will call it a spongy bone sandwich. Okay, one way of thinking about it here. That's the intramembranous. I mean, you can't really, this is what it looks like underneath the microscope here or here. Basically, I've got spicules of bone. We don't show it generally at the stage where it's getting the cortical bone on the outside of it. We show it at this stage right here. And how you recognize it, I've got spicules of bone. If I take a look, see I've got cells lined up on each side of the spicules. Okay? Each side of the spicules has this osteoblast lined up. I mean, let's go a little higher power. Spicule, inside, outside. That's telling me that this is intramembranous ossification occurring here. Spongy bone, and not just, if it's just sculpting bone, if it's growth of bone, we'll talk about it only being on one side, not both sides of the spicules. I'll talk about that when we get to it in just a little bit here. Okay? Now the one that is given a lot more time in textbooks is one that we can see underneath the microscope a little bit better, that being endochondrial ossification. Endochondrial ossification, start off with mesenchyme, but it converts this, let's say, is one of your phalangeal bones, one of the bones here in your fingers. Now realize, oh, they're so short, they're short bones. No, you look at the structure of them, they're long bones. Okay? I always tell students, if we're thinking of a long bone, if I told you in a cartoon to draw a bone that the dog had in its mouth, you draw a long bone, right? Epiphyses on each end, diaphysis in the middle. Doesn't matter how short it is, that little tiny bone right here, the distal phalange of my little finger, is still a long bone. Okay? That's what we're looking at right here. It's originally made from mesenchyme as a piece of cartilage. Okay? Hence endochondrial ossification. Let's talk about the sequence of events that's going to occur here. First thing we're going to get is you're going to get hypertrophication of the cartilage cells. Hypertrophication means what? Getting larger and dividing. Okay? Proliferation, hypertrophication, and there. Dividing and enlarging. You have less matrix, Going to be a lot of lacunae packed very tightly on top of each other. And then what's going to happen, they're going to do that right along the edge of the diaphysis, and then you're going to put calcium salts into the matrix of that hypertrophied cartilage. Now, calcified cartilage does not equal bone. Okay, that's just something students have thought over the years, I can tell you. Oh, if I take cartilage and calcify it, I've got bone. No, you don't. Still not bone tissue yet. But once we have that blood vessel, we first do that here in the bony collar, a collar around the diaphysis. Once we have that, blood vessels can infiltrate. Remember, blood vessels do not pass through cartilage, correct? It's avascular. Once we put the calcium salts in there, we can put a blood vessel. Blood vessels can infiltrate in. And when we do that, we can now convert cartilage into bone. Okay, and that's conversion there is converting osteoprogenitor cells and so on. It's not just cartilage converts directly to bone. We replace the cartilage with bone tissue there. We refer to that as a periosteal bud when that blood vessel infiltrates, like right there. Now, more important thing here, if you take a look, we do it first within the diaphysis and then within the epiphyses. We don't necessarily do those in the same order. We did this in the proximal epiphysis and then the distal epiphysis. That's generally the order in which we do it. But we refer to it because it happens first in the diaphysis. That's the primary ossification center. The epiphyses, even though they aren't at the same time, those are the two secondary ossification centers. Okay? Primary ossification centers, secondary ossification centers. And if we take a look, the blue is a cartilage. Even down here, mature bone, we're going to leave a little bit of cartilage on the end, here and here. Those are the articular cartilages we talked about. But prior to that, we're going to leave a little bit of layer of cartilage here between the epiphysis and the diaphysis. Metaphysis, I don't know if you've used that term. I'm not going to use it, but you'll see it sometimes. That's the junction right there. You see we did it here. Once we've got this distal epiphysis, we do it right there. That is called the epiphyseal plate, or the growth plate. And we'll look at that a little bit later. And that is where long bones can grow longer. Now eventually, we're going to fill that up with bone, and it will be an epiphyseal line right there. We'll come up to that and I'll show it. But you can see an epiphyseal line I'm tracing right over with my pointer. Okay? And at that point, we can no longer get any longer at this end. This end is still able to grow a little bit longer because it still has an epiphyseal plate, or that growth plate, in layman's terms, right there. All right? And here we can kind of see some of the process. I mean, we can talk about layers in more detail that we're not going to go into right here. But here I can see I've got diaphysis would be down here. Here's my secondary ossification center being ossified. Still got a good bit of cartilage up there. But here is my epiphyseal plate right here that will allow that long bone to grow longer. Well, once again, we'll look at that in just a little bit. All right, next thing to talk about is reformation. That's the idea that bone is constantly being remodeled throughout your lifetime. Okay? Now, if we're remodeling something, if you watch HGTV and one of these, house remodeling shows, what's the first thing that they have to do when they decide to remodel? Demolition, right? You watch Chip and Joanna. Chip gets crazy on the demolition, right? If you've ever seen him, okay? Takes a wall and runs through it or something silly like that. But demolition, you've got to tear things down. Who's the demolition specialist cell-wise in bone? Osteoclast, okay? This is bone being remodeled, spongy bone. But here's osteoclast on one side. Once you've had some demolition, you've got to build back up. Who are the cells that build back up? Osteoblast, here they are on this side. And when bone is being remodeled, you can think of sometimes as growing as well. you're going to see osteoblast on one side, and you may not always see osteoclast like this, but the osteoblast will just be on one side. Think about your skull. As your skull gets larger, here it was when you were born. As your skull has gotten larger, you've had osteoblasts laying down more bone on the outside, but you have osteoblasts taking away bone on the other side. Otherwise, your brain would still fit in here, right? In your skull, your bone would be that thick. You see my point? That's why I got osteoblast on one side in this image, osteoclast on the other. And that's different than when the bone forms, because I said you see osteoblast on both sides of the spicules. When you see it on one side, that's not endochondral ossification. That's some type of growth or remodeling occurring. Okay? And bone's constantly being remodeled. We talked about this in physiology, I know, because you can remodel it larger and more dense in terms of calcium hydroxyapatite till about 30 years of age. And then you remodel it smaller and smaller. That's why we want to maximize bone early in life. But bone's being remodeled. We can talk about things such as, used to be we talked about braces on kids. Now we need to put braces as adults. You've got two sitting in a bony cavity here. Bone's constantly remodeled. There's several factors you talked about in physiology. Calcium availability is one, but mechanical stress placed upon bone is another. If I've got that bone sitting in a bony socket and I put rubber bands or wires making it turn or move, as that bone is remodeled, that tooth is going to straighten out, isn't it? We're going to move to where we want it to move. Bone's constantly being remodeled. A lot of different factors going into that. I won't go into all of them. Okay, that's more of the physiology talking about that. Certainly has applications in terms of clinical medicine. All right, let's talk about bone growth. And the growth of the flat bones I've kind of hit upon because it goes right in with remodeling here. Just simply we're going to add osteoblast on one side, osteoclast on the other in terms of the growth of flat bones. For long bones are where we want to talk more about it. And long bones get longer, but they also get larger in diameter. The diameter of your humerus now is not as much larger than the diameter of the humerus when you were born, correct? And so that's the appositional growth, and that's what this image is talking about. And once again, it's what we were talking about earlier. You're going to have osteoblast on the outside here laying down new bone. Idea shown with the blue arrows, but you're going to have osteoclast on the inside making that medullary cavity larger. Yeah, you're going to get a little bit thicker in terms of the layer of cortical bone from here to here, but it's not like you still have this tiny medullary cavity and a huge thick layer of bone. Once again, that's because the osteoclasts are taking away bone from the inside. That's appositional growth. The one we talk about more, though, is the longitudinal growth. And this is one I had the idea for a long time how I'd make the image, but if I can't do it in PowerPoint, I don't have the artistic ability. There's images like this I hunt for sometimes for years online before I found them, and this is one. Okay, it displays a concept here in terms of how long bones get longer. Okay, let's talk first about. We'll talk first about the zones. Let's look at it right here. Basically, what we're going to have here is my epiphyseal plate right here. What's going to happen is on this end, on the upper end here, it's going to increase. This end right here, bone's going to be growing in this direction, taking it over. Okay? And that's what they're trying to show you right here. We'll talk about the zones and what's happening here. But what happens here, 6 months ago, this was where the epiphyseal plate ended on the epiphyseal side. Okay? Epiphysis is up here. We looked at it 6 months later. If we come across, it went from here up to here. Okay? But made the long bone grow that much more. Okay? If we look down on this side, here's where cartilage and bone meet. We come across, that's now all bone. Here is corresponding layer moved up here. What I always like to say is if this is growing in this direction at 20 miles an hour, and the bone is coming up at 30 miles an hour, what's going to happen? Eventually the bone's going to take over all the cartilage, correct? We'll have no cartilage left, we have no epiphyseal plate left, it'd be an epiphyseal line. At that stage, you're done growing, or your fingers are done getting longer, but you're done growing any taller. Okay? That's basically the concept of what is happening. The cartilage is growing, it's getting thicker towards the ends, because towards the middle part there, towards the diaphysis, cartilage is being converted to bone. Okay, but what I was looking for was something that showed if we go across here, 6 months later, this is higher, 6 months later, this is higher. Okay, now let's look at it as it's normally taught underneath the microscope. Image, I don't know if this is your textbook or a different textbook, but if we look right here at these phalangeal joints, take these proximal phalanges, you can see here's a bone, that proximal epiphysis, there's a line right there, that's the epiphyseal plate. Okay? So the fingers are still getting longer. And then if we looked at that epiphyseal plate, with this being the epiphyseal end, this being the diaphyseal end right here, this is cartilage up here, and then the cartilage from here to here looks very different, doesn't it? And we've got zones in there. The zone up here is a zone of resting cartilage. That's just normal cartilage. It hasn't started elongating yet. Okay, the zone of reserve cartilage is right there. And then we're going to have the zone of proliferation. Proliferation meaning cell division. See, these cartilage cells are kind of just scattered about. Here, as they begin to divide, they look like they're stacking on top of each other. As one divides into two, the two stack on top of each other. As they divide again, 2 into 4, the 4 stack on top of each other. So they stack up on top of each other and make lines here in this zone of proliferating cartilage. Once they're done with that, the cartilage cells are going to increase in size. Lacunae are going to increase in size. Look at the size of lacunae above my pointer here. These you can make out the cells and lacunae individually. Up here you really can't because they're so small, correct? So first they proliferate, then they get larger. Then you're going to calcify it. As you calcify it, the cells are going to die. And then you're going to have a zone of ossification, sometimes called the zone of provisional ossification, where you're converting into bone. And so basically, if we look 6 months later, these cells here, they're in the zone of resting cartilage, would actually be in zone 2. It's moving up here. This zone right here, a zone of ossification, would be up here higher. Okay? And that's how it's getting longer in this direction, because see how these are elongating? What was one little section, say here, the thickness of my pointer in the halo? Now it's, here proliferating cartilage, is 4 or 5 times thicker. And that same layer up here, layer up here, we get down here, you go from, if this layer right here, let's say that's distance of my halo, pointer and halo, gave rise to all of this thickness here, we've definitely increased the length of the bone, haven't we? Okay, that's how long bones get longer. All right, you do not have to identify the zones. Where you mark the zone, one beginning, one ending, this is about as good as it gets, okay, in terms of the image right here. Know the zones, know them in order, understand the process. Okay, that's where I wanted this slide to kind of show the process a little bit more. All right, any questions? All right, no questions. I'm going to stop right there and switch to the lab slides, and we'll go through those. All right, looking at cartilage. All right, when we look at something like this, chondrocytes inside lacunae, one of the things that gives it away is when I see the lipid droplets in there. Right above the pointer, you see that huge lipid droplet inside that cell? These are chondrocytes inside lacunae. If I look here where I see matrix, I get no hint of fibers in there. That's going to make that hyaline cartilage. Or on the outside in the pink is going to be my perichondrium, and these flattened cells just deep to the perichondrium will be chondroblast. a little bit larger here, chondroblast, or reserve chondroblast, either way. These are chondrocytes. Lacunae is when I can see the opening. I mean, normally the chondrocytes in the living cartilage fills up the entire lacuna. It's only when they shrink that we see the chondrocytes inside the lacuna. I'll point those out. Some slides are coming up. All right. Lower power magnification, but even here, I can make out the idea. Look at that lipid droplet right above my pointer. See that little white light? That's that lipid droplet in there. The lipid's gone. But chondrocytes inside lacunae, perichondrium. These would be my chondroblast right here. All right. Higher power magnification, probably the same slide. Perichondrium, chondroblast, okay. And then see the lipid droplets in here. These are the chondrocytes that don't really make out any lacunae. I don't see any that have shrunk up, maybe other than this one right above my pointer here, and that's more of a chondroblast shape of the cell. All right. This is what you typically will see a lot of websites and so on. I mean, this is one they really took the time to make this look like it did for a textbook. Okay? This is more like you'd have in a lab or even a pathology lab. All right, if I take a look, definitely a connective tissue, right? Because I've got a lot of matrix in here. Only thing that looks like this would be chondrocytes inside lacunae. Look right here, right above it. See that white area? That chondrocyte really shrunk up, so you see part of the lacuna, don't you? Okay, artifact of the preparation, because it normally fills up that entire lacuna. Okay, perichondrium right up here, the flattened cells, like right above my pointer here, would be a reserve chondroblast. All right, if I look at that matrix, I don't get the hint of any fibers in it. Hyaline cartilage. On the other hand, look at this. Wish it wasn't labeled, but look right above the pointer. I see a lipid droplet. Must be a chondrocyte. It really shrunk up, didn't it? I can see the lacuna all the way around it. Chondrocytes inside lacunae. If I take a look around lacunae, see how there's like a black halo around them? And then that black halo, if I look out here in the matrix where I don't have as many chondrocytes, I really see some black fibers, don't I? Black fibers tells me elastic cartilage. Okay, still got a perichondrium, still got that layer of chondroblast right here, flattened out. But this is the one, either I don't know if it's harder with elastic cartilage or they just didn't take the time to make it where the cells don't shrink up, and the chondrocytes really show lacunae, don't they? They really shrunk up a lot. But it also kind of helps it because we see that black ring around lacunae, and then we look for the black lines in the matrix. That tells us that's elastic cartilage. Okay, that was an extraordinarily good image before. If they're going to put a 5 out of 5 in a textbook, this is a 3 out of 5. Okay, you'll see this. I'll show you better than this, but once again, you go to different websites, even a few textbooks, they're going to show something like this. Once again, if these are cells in here, you can get the idea like, there's a nucleus right there. It's connective tissue because I've got matrix in there. Around, I see black rings around the lacunae, and right in here, let's say I've just got matrix, no cells. I can see black lines going through. Overstained a little bit there. I'm going to give you something better than this, but you're going to see this as you look at other sources out there. All right, very, very high power right here. First of all, it is a connective tissue, isn't it? Got a lot of matrix. Here's a chondrocyte, it shrunk up, so chondrocytes inside lacunae. See a little bit of a lipid droplet there, a little bit of a lipid droplet here, but if I look around lacunae, I've got dark rings, maybe not that well defined, but I do have some dark rings. And then when I look in the matrix, I see black spider-like threads, don't I? Okay, that makes that elastic cartilage. All right, if I look at something like this, first of all, it's a connective tissue. I've got well-defined cells. It can't be ligament, tendon, where, the cells don't look like this here. I don't really see them that much inside lacunae with this, but I really get the idea. There's a lot of fibers running through here, don't I? If this were ligament or tendon, the cells are going to be flattened a lot more. These are plumper. This is fibrocartilage. Okay? Now fibrocartilage also, if we look at the pubic symphysis is one place we often see it. It's one we often use as a source from a show fibrocartilage in a textbook or website. The pubic symphysis, it turns out you've got one layer of fibrocartilage where the fibers are coming like this, another layer where they're coming out like this, and they're alternating layers. Okay? If you work with wood at all, a piece of plywood is made that way in terms of grains going at perpendicular 90-degree angles with each layer. Okay? And that's what we've got right here, except rather than being like this, they're like this. Okay? So they're not perfectly coming out of a cube, not perfectly right and horizontal, but here's the one, this layer right here is coming out at an angle. This layer is horizontal to you, but not quite. A little bit of an angle there. Coming out at an angle, running through the screen at a slight horizontal at a slight angle. You look down here, I can get the idea. First of all, I know it's connective tissue. Look right here, I can see a chondrocyte inside a lacuna, can't I? And then when I see fibers in there, here's fibers running horizontally, here's fibers coming out of the screen, and they're not perfectly right angles either way. Horizontally, coming out of the screen, that's fibrocartilage. Okay? In other words, it doesn't always have it where they're all going in one direction parallel to each other. They can have layers to it. Okay? All right, osteogenesis. All right, nice trichrome stain right here. Now, if it's osteogenesis, I'm not going to have 5 choices there. Name the process occurring on this slide. It's either intramembranous or it's endochondrial, correct? Spicules of bone, got to be intramembranous, correct? Now we can name some other things here. You'll name the cells right here. They're labeled for you. Along the surface, large cells along the surface, not distinct. Could have done this layer right here. Okay, that's going to make those osteoblast. Cells right here, above my pointer here, above my pointer here, on either side below my pointer. They're surrounded by matrix. That makes those osteocytes. What's the name of this blue layer right here I'm tracing through? That's the osteoid, right below the osteoblast, correct? Okay. Don't have any osteoclast in here, but that's not unusual. Okay. But osteoblast, osteocytes, I can say, name this entire structure here. That's a spicule of bone or trabecula bone. Okay. All right, if we take a look at this slide right here, H&E, so we aren't going to see osteoid, but if this is bone, I have osteocytes inside lacunae. How do I know this isn't cartilage? How do I know it's not chondrocytes? You're never going to see things like this. Inside, there's a blood vessel. Doesn't happen in cartilage, correct? And so this is bone, spongy bone. This layer right here, right along the outside, long, large cells. I can label a line right here. Osteoblast, osteocytes. Do I see osteoclast? None that really give me a good look of an osteoclast right here. All right. I see something like this, and I ask you what name the process going on. A and B. Endochondrial or intramembranous. Look at this. Boy, I may not recognize it, but there's no spicule of bone there, is there? No trabeculae of bone. What I've got, this is bone down here. This is cartilage up here, which is hard to say, but you can kind of make out chondrocytes inside lacunae right here in that zone of hypertrophication. And that's even on a 4th slide like this, and this will show up, a slide like this will show up in a textbook. So I'm not making you know the zones. The one I showed you was a perfect one I found from a textbook. This one's a lot harder to label, but you can make out the idea that this is definitely, I'm only asking you, only 2 choices here, intramembranous or endochondrial. Here I can see the idea of cartilage in here, and it looks nothing like that, does it? Okay. Next slide, a little bit better slide right here. Here's bone, I can see red marrow in here. I can make out right here, even right in here, I can make that out as being cartilage and being hypertrophication. It's actually being where it's transitional ossification. Right here would be hypertrophication. look right along the edges and see if you can't get a hint of cartilage in there. Cartilage stacked on top of each other in terms of chondrocytes. Right along the edge right here, you can get a hint of that, and that tells me, even though I see spicules, too much other stuff going on in here, and that tells me this has to be endochondral ossification. This is a decent slide of it right here. Once again, you can get the idea why I don't make you identify the zones. All right, let's look at some dry ground prep, so what we can identify there. You know, if I circled this right here, and it's off the screen, I am circling a blank, an aversion system or an osteon. Name the dark structure the pointer is in here. Be an aversion canal. What travels through aversion canals? Blood vessels and nerves. Not always nerves, but most.